Yeah. Okay. So you can go ahead with your doubts first, whatever doubts you have.
Sure, sir. Sir, for
Yeah.
week 4 assignment, sir. Sir, for week 4 onwards, from week 7, it is continuation only, no, sir. Only one top bike from bike code. Previously, we saw full swing. Now you are discussing about noise. 6th week and 7th week.
Yeah. Correct.
Okay, sir. That for week 4, for question number 2, I have doubts, sir.
Just a minute. Let me share that screen. So yeah, can you see my see the course web page on my screen?
Yes, sir. Yes, sir. Yes, sir.
Yeah. So in week 4,
Question number 2, sir. And first question, second part also, sir. That matter,
okay.
could you please explain about it, sir, in detail?
So the okay. So let's start with the first question, second part. What we have over here is a low pass Butterworth filter needs to be designed that satisfies these things. That you need DC gain of 1. Okay, I will put it on my uh, workspace, and then we will go from there. So yeah, can you see my iPad screen
Yes,
now?
sir. Yes, sir. Yes, sir. Yes, sir.
Yeah. So what we have, we need to design a Butterworth filter that satisfy following things. So first is that the DC gain should be 1. Other is that the gain at 1 megahertz should be at least 0.95, and then gain at 2 megahertz should be at most 10 to the power
One.
minus 1.
Yes, sir.
So how does this frequency response looks is, so we have 1 megahertz over here and 2 megahertz over here. So DC, it should be 1, and let's say this is 0.95. So it should go something like this, and then this is, let's say, zero point 0.1. So it should be something like this. So determine minimum order needed and corresponding 3 dB bandwidth of the Butterworth transfer function. Plot the magnitude in dB scale. So I hope this part is okay for you, right?
Yes, sir. Up to here, okay, sir.
Yeah. Next part is, suppose 3 dB bandwidth data, above data
Sir,
varies by plus
if
minus.
sir, if time passes, could you means in detail you go, sir. First for first part also, it would be revision for me also. I'm enrolled for exam also, sir. April 29th.
Okay, sure. So how to proceed with this is, so we know that so Butterworth, any so say nth order Butterworth filter, what is the frequency response? We have 1 upon 1 plus f over f naught into 2 to the power into to the power 2 of n, correct? Uh, and its square root. This is the frequency response that we have for a Butterworth filter, right?
Yes, sir. Yes, sir. Exactly. In
Yeah,
sir, professor said in angular frequency, you change it to frequency domain.
yeah, correct. So if we, even if we write it in angular frequency, so angular frequency will be 2 pi f divided by 2
That
pi
will
f
cancel.
naught.
Hmm.
So 2 pi will cancel. So we can just write it simply in f. And since in question it's written in hertz, so we will proceed with hertz. So you should be careful actually. Here it happened because the bandwidth also had 2 pi, and the argument of omega also had 2 pi, so that got cancelled. But let's say it's so you should be careful. Whether you have to put 2 pi first and then cancel it. I wrote it directly, but just be careful in the exams.
Oh, yes.
Okay, so DC gain is 1. DC gain of any order is 1. So that I think is not an issue. After that, what we have is that a point, it should be less than 0.95. It should be greater than 0.95. So one constraint that we have is 1 upon this complete transfer function f upon f naught to the power 2n should be greater than or equal to, and here it comes f as 1 megahertz, 10 to the power 6 should be greater than or equal to 0.95, correct? And the other constraint is that at 2 megahertz it should be less than 0.1. Okay, so other constraint is one plus 2 into 10 to the power 6 by f naught to the power 2n must be less than or equal to 0.1. Okay, so what do we have from here is that so what we need to find, we need to find the f naught, that is the 3 dB bandwidth, and the order of the function, that is n, correct? So now the minimum order of the function, and so we want to achieve this in minimum complexity possible. So instead of having this inequality, we will have it as equation. So let's say we will go for the whatever minimum is possible. So we'll have it as equation. Now we have two equations and two unknowns. So we will try to solve this. So what do we have? What do we have from here is so the first part is 1 plus 10 to the power 6 upon f naught to the power 2n is equal to 1 upon 0.95, correct?
Yes, sir.
And so 10 to the power 6 by f naught to the power 2n is equal to 1 upon 0.95 minus 1. So you can be sure that this quantity will be always greater than 1. Why it will be greater than 1? Because at DC the value of the transfer function is maximum, and after that it is just falling. So and this is at some random frequency. So definitely this number will always be greater than 1. Greater than 0. So you have one constraint here as follows. Just a minute.
Yeah. 0.05, sir.
So this value is 0.05, is it?
Yes, sir. 26, sir, exactly.
Okay. 0.0526. Okay, thanks
Yes.
for that. And other constraint that we have is two into 10 to the power 6 upon f naught to the power 2n is equal to 1 upon 0.1 minus 1. Okay.
9, sir.
So this is 9. Okay. So first thing that we can do is so first of all we need to find the order, right? So we can divide equation 1 and equation 2. So we get from there as to the power 2n. So if we divide equation this, let's say this is equation 1, and 2 into 10 to the power 6 upon f naught to the power 2n. Let's say this is equation 2. So equation 2 by 1 if we do, so we get 2 into 10 to the power 6 upon 1 into 10 to the power 6. F naught and F naught are cancelled. To the power 2n is equal to 9 divided by 0.0526. Correct?
Yes, sir.
Yeah. So finally, what we need to find is
N.
2n is equal to log to the base 2 9 by 0.0526. Okay. That means n is equal. So here n will come as some fraction.
8, sir.
However,
Round of
so
8.
it will.
4.
Yeah, no. You don't need to. You shouldn't do round off. That's what. You should never do round off, because you should keep in mind that we started from inequality. We need to satisfy this inequality. So doing round off will create issue. So let's say it comes as a 7.9. Say the your n comes as 7.9 or 7.1. In both these cases, you should take n is equal to 8. Why? Because if you need to satisfy this inequality. Okay, so let's say in this case you choose to take 7. In this case, this inequality won't be satisfied. So you won't be able to meet the design spec. So whatever value whatever value you get of n, you should always take a number higher than that. The greatest integer function, basically, you have to apply on that. Is it clear?
Yes, sir. Yes.
Yeah. So this you should always keep in mind. You shouldn't do round off. You should do a greatest integer function, so that you can get the maximum value of n possible. So this value, if you calculate, you are saying you get 8. Okay.
Yes,
So
sir.
we will cross
No,
check
sir.
it once.
By 2n. By 2, sir. 4 will get.
Okay. Just a minute. We'll calculate it
Yes.
quickly. So if so here you got this thing by 2, 2n is equal to this thing. So generally, if you want to calculate the logs of some random base, I hope you will be knowing this. So you can calculate log of e divided log of log to the base e of this divided by log to the base e of 2. So this and this are equivalent. I hope you will be knowing this from your theory of logarithms and all.
Yes, sir.
So 0.0526, and we have to take its log. So let's say we have log 10 over here. So this comes as 2.233 divided by
7.32 approximately.
7.4, something like that.
Yes, sir.
Okay, so
I round off it as 8, sir.
so n. No, that's what you should take. So first divide it by 2n and then take the value. Then take the greatest integer function.
Yeah.
Okay, so 3.667 or something like that.
Oh, okay, sir.
Yeah. Okay. So n should be greatest integer function of that, and that should be equal to 4. Okay. So this is done. Now you can easily calculate the f naught from here. How will you calculate f naught? Let's consider this equation only. And again, f naught, that whatever you calculate from here will be basically like the minimum value possible. Sorry. So the f naught will be somewhere between 1 megahertz and 2 megahertz only. So this you can keep it as a check. Whatever f naught you get, if it is not coming in this range, then you might have done some error in your calculation. So you can keep that as a check for you.
Sanity check. Yes.
So let's consider this equation only. Yeah. So let's consider 2 into 10 to the power 6 divided by f naught to the power 8 is equal to, so what you get from here, 2 into 10 to the power 6 by f naught is equal to 9 to the power 1 by 8. And that you get as, this is what your f naught is. So let's try to calculate it. So 9 to the power 1 by 8 is 1.31. Sorry?
Okay. Sir, I'm getting 1.5196, sir.
Okay, the final answer you are talking about, is it?
Yes, sir. After taking the whole
Uh,
thing in megahertz, I'm saying, sir. That 9
okay, just a
1 by
minute.
8 is 0.125, sir. 9 power 0.125 inverse into 2, I got 1.51.
Yeah, yeah, yeah. So this comes out to be 9 to the power 0.125
Yes, sir. Inverse and
inverse
into
of this and
2.
multiplied by 2.
Yes, sir.
Yeah, 1.52 something, 1.52 megahertz.
Yes, sir.
So I hope this is done. So let's move to the next part.
Sir, here we okay. Here we will take only 2 values, sir. We have to take 3 values, sir, up to. Means it is
Sorry.
megahertz.
Uh,
It
yeah, so anything like whatever is mentioned in the question, you can use it. If nothing is mentioned, like you can take any value, like you can take up to 2. So it doesn't matter. So next part is, suppose 3 dB bandwidth determined above varies by plus minus 5%. What does need your order need to be for response to still satisfy this requirement? So what we did previously is we assumed that nothing varies, and in that case we converted our inequalities into equalities. Correct. However, in this case now we can't don't have that luxury. So let's found. So these are the two. Let's get back to this. Now, what we are said is, let's say it varies by plus minus 5%. Okay, so for the first inequation, what will be the worst case of what is better, f naught being higher or f naught being lower to satisfy the first equation?
F naught should be greater than or equal to, means it should be.
No, I am saying, let's say f naught you calculated as 1.52 megahertz. Okay, this is
Yes,
the critical f naught, correct?
yes, sir.
Like for an order of 2, for an order of 4, when f naught is this thing, you get exactly 0.95. Now, in
Yes.
what case, in which direction f naught should move that you still satisfy this equation?
Means it should be in this range, sir. It means it should be in 0.95 and 0.1.
No. I am talking about f naught. I am not talking about the overall magnitude. I am talking. So what basically our magnitude response now looks like. So it starts from 1, the 0.707, that is the 3 dB bandwidth, occurs at f naught. Okay. And in 5 kind of response. Okay. So what happens if f naught moves further? Will our will our first equation be still valid or not?
Sir, can you repeat again, sir? Between voice didn't came, sir.
Okay, what I'm saying is, like, you have this, this you understood, right? The
Yes, sir.
magnitude response side. So for the 1 megahertz is somewhere over here, and for the the values of f naught and n we calculated above, this thing holds true. Okay. Now, what I'm saying is, let's say if like your order remains the same, it's fourth order. Like order cannot vary because that is basically the design choice. Like that is the number of op amps you have or number of capacitors you have in the circuit. That cannot vary. Okay, only your F naught can vary with the component variation. So what I'm saying is, like if the F naught moves further away, like if F naught increases, will the first constraint be still valid or not?
It won't be valid, sir. Why means
Why?
means it vary means that means
I'm not talking about random variation. I'm talking about when it increases.
sorry. You continue, sir. I, my answer
So,
is if it increases means there will be a variation, sir. Won't
no,
remain
no,
same.
that your variation will be there. But what I am saying is, what if F naught increases? F naught increases means your 3 dB bandwidth moves to higher frequency, correct?
Yes, sir.
So
Exactly.
let's say F naught, the new F naught is somewhere over here. Okay. So how will your curve now look like? So it will start from here, and the 3 dB bandwidth will come at F naught, right?
Exactly, sir. Uh,
Okay, correct.
mm,
So my question is, in the violet line, is the magnitude at 1 megahertz still greater than zero point 0.5, right? 0.95, right?
exactly, sir. Yes, sir.
Yeah. So that's what I'm saying. Like F naught increasing is not an issue for satisfaction of this constraint. Correct?
Yes, sir. Exactly, exactly, sir.
Yeah.
Mm,
Now, what is the worst case? So we said that the calculated F naught, sorry, we said that whatever F naught we choose can vary from plus minus 5%. That means F naught can be either zero point 0.9. So you, let's say you choose some value F naught. So actual value of F naught in the circuit can be some 0.95% of the chosen 0.95 times the chosen value, that is minus 5%, or some 1.05 times the chosen value. Correct?
yes, sir. Exactly.
Yeah. So, which of this will be a problem for our first constraint? The 0.95 times F naught or 1.05 times F naught?
0.95 F naught, sir.
Correct. So, this will create your worst case, right? So, in
Exactly, sir.
equation 1, you should replace F naught with 0.95 times F naught. Okay. 1 plus 1 into 10 to the power 6 divided by zero point 0.9, sorry, to the power 2n must be greater than 0.95. So this is the first equation that you get to solve your second part, right? Now let's come to the second inequation. Now in this second inequation, can you tell which is the worst thing, 1.05 F naught or 0.95 F naught? Based on the discussion so far, can you extrapolate this fact?
1.05 F naught, sir. For
Why?
second equation, it is less than that's
Yeah,
why, sir.
yeah, correct. Basically, let's say again, we if we extend this curve something like this, so here will be some 2 megahertz, correct? And
Yes,
if
sir.
this is zero point 0.1, so this will be greater than 0.1. So f naught increasing is a bad thing for the second constraint, right? So the second inequation becomes
2 into 10 power 6,
2 into 10 to the power 6
6
divided
by
by
1.05
1.05 times F naught.
less than, okay. So,
0.1. So now the same way that you solved this in the first thing, again now you can now since you have the worst case scenario for both the inequations, now you can convert them into equalities and solve for f naught and n, because now like again you will have two equations and two unknowns. Okay,
same like previous
so
things.
just you needed to yeah. Same thing, just the only modification is now you have these coefficients with f naught. This is
Yes.
to accommodate the worst case variation that the question was providing. So the worst case for the first constraint, that is like at the band edge, your your signal should be greater than your gain should be greater than some value. For that, the worst case is that your center frequency is decreasing. That means your bandwidth is decreasing. And for the second constraint, that in the band stop, your response should be less than some value. In this, the worst case is that your central frequency is increasing. So based on that, you got these coefficients, and now you can proceed as you proceeded in the first question,
Yes, sir.
first part.
Yes.
So I hope it is clear now.
Yes, sir.
Okay. So the second question also you asked for, right?
Yes, sir. Sir, one more thing, sir. For first question only, sir, could you please
Yeah.
explain about MATLAB also, sir? In final April exam, there is chance to ask code, sir. MATLAB code, MATLAB plot, sir.
In the final exam, I'm not sure. I don't think there will be. MATLAB is mainly for your own understanding. However, I will get asked from the regular TAs and let you know like how the final exam will be. But I'm not sure as of now. But still, you should do these MATLAB assignments so that passing the exam is one thing. You are trying to do this course to actually be able to design circuits or
Yeah.
design systems. So for that, you should know MATLAB. You should try that uh, example as well and paste it. Uh,
Yes, sir.
d- yeah.
Sir, one more thing, sir. Can you please guide me, sir? What are the steps for MATLAB? Sir, I will after that also I will watch this recording, sir. At the time, it will be useful for me.
So I won't be going through the exact code. I can just show what all you need to do. So what you need to do exactly is you need to plot the response to show that whatever you are showing, whatever you are saying is correct, right? How will you justify it? You will have to justify it by plotting the response, correct?
Yes, sir.
So for plotting the response, what all do you need? You need a frequency axis, correct? And you need to find the magnitude response corresponding to that frequency axis. So you can take a variable of n, that is your order. You place it as 4, let's say. Okay, your value of f naught. Okay, that can be any number or whatever you calculate, correct? So let's say in the second part, the f naught you calculate is some, let's say, I'm not sure, it's just a random guess. So it's a,
1.52,
so
like
the
this.
order will be slightly higher, I think, because now you have variation. So let's say the order comes out to be 6 and f naught is somewhere around 1.5 only. I am not, again, this is not the answer. This is just a illustration. Okay. So you have these two variables. Now you need to find the frequency. Now you need to make the frequency axis. So frequency axis you can assign with a variable called f. So you can, since you need up to 2 megahertz, so let's say you will plot up to 4 megahertz. So what you can do is you can take steps of say 100 kilohertz. Okay, 100 kilohertz I think will be a little too coarse. Let's say you take steps of 50 50 kilohertz, so 50 E3, 50 E3, and you go all the way up to 4 megahertz. So it's 4E6. So you created the frequency axis. Now you need to create. Now what you need to create? You need to create the magnitude response. So how do you create the magnitude response? Let's say there is another variable called capital H. So this will have 1. And mind it, in MATLAB, if you want to do the division of a vector, so in that case, you can't simply put it like this. It will do the matrix multiplication or matrix approximation, if you or a matrix operation on that. If you want element by element, for example, there is a array that has 1, 2, 3 in it. There is another array that has 4, 5, 4, 6, 8, 7 in it. Okay. So let's say you want to do a division of 1 divided by 4, then 2 divided by 6, then 3 divided by 7, and you need to store them in like a separate element of an array. So like you need to divide this, and you need to get an array that is 1 by 4, 2 by 6, and 3 by 7. So in that case, you shouldn't do like a regular division sign. You should put a dot and then put a division sign. Same goes with multiplication. Same goes with exponentials. Is that clear?
Yes, sir. Yes, sir. I'm listening, sir.
Yeah. So now how does it goes? It has 1 plus f by f naught. Again, here again, you have to do element wise exponential. So you will put the dot, then operator, exponential operator, then you will put 2 into n, then close the bracket. So this will give you the magnitude response. Yeah, correct. So let's say we call it some h2. The h we can call as square root of h2. Okay.
Sir, so small doubt, sir.
Yeah.
For power, we will use that cap, no, sir. For square root, what symbol we have to use, sir?
Yeah, this is the cap. So either you can do cap 0.5, or there is a function called sqrt. You can use this.
Okay, that is keyword, sir.
Yeah, that is keyword.
Oh, okay, sir. Continue, sir.
That is a function in itself. Sqrt is the function in itself. You can do it either way. You can take dot cap 0.5, or you can do this. Anything will work. So next comes is then you have to plot this function. Okay. So you will put a hold function, hold on, and then plot frequency versus the magnitude. So what you can do in the final plot, what you are to show in the final plot. So let's say first of all you take f naught as the one you calculated in the second question. You plot it, and you show that at 1 megahertz, whatever you have is greater than 0.95. It should be greater than 0.95. Then you put here and at 2 megahertz, it should be less than 0.1. Then you put over here as the lower most value, 0.95 times whatever you get. In that case, you should plot this complete thing again. So it will look something like this. In this case, this should be exactly equal to 0.1, and this should not exactly equal, because order what you calculate, you are using greater than 1. Again, they should be greater than 0.1. They should be less than 0.95. And so finally, you put as 1.05 over here. And there you show this curve. So here also it should be greater than 0.95, and this should be less than 0.1. So if you plot these three curves, you will verify that like even in the worst case scenarios, your the constraints that you have for the design are matching.
Yes, sir. Good, sir. Thank you so much, sir. Next question, sir. Here, for in that
Okay.
problem two, sir.
So
Uh,
yeah,
Problem two, the professor explained, sir, the band pass node and low pass node. Sir, for how you comment about
correct.
band pass and low pass, sir?
The band pass and low pass depends. You can comment based on the frequency response. What exactly you want over here? Determine. So it is excited by this thing. Okay, this is a little involved question. So we can't do it in frequency response. I will show you how it needs to be done. So I will give you some hint. I won't show you the exact solution for this. The hint is that you should not check the frequency response. How the if signal passes through a filter in time response, how do you calculate the output of that filter? Let's say there is some time waveform, okay, and there is a filter, and you have to calculate the output of that filter. So how will you calculate the output of that filter in time domain, not in frequency domain?
Filter means we will find out the output by input, sir. Transfer function, output voltage,
No, no,
transfer
no.
function.
This is frequency response. I'm not talking about frequency response. Or a Laplace domain. Forget about Laplace domain and frequency domain. I'm talking in time domain. What is the characteristic of what is the unique characteristic of a filter in time domain? So in frequency domain, it's frequency response, right? In time domain, what is it?
What
Correct. In time domain, it's impulse response, right? So if let's say there is some input to a filter, how will you find the output to that filter? Given that you have the impulse response of that filter.
Convolution.
Correct. Yeah. So you need to find some waveform x of t that when convolved with the frequency, the magnitude, the impulse response of this, say h of t, that gives you the maximum value at some part of time. Now, the hint for this you can take is how to do convolution. One is the mathematical way, like integration of x tau into h t minus tau d tau, correct?
exactly?
And the other way is the graphical way. I hope you have learned it in signals and systems course. There is a graphical way
Convolution,
of doing it. That
circular convolution.
not the circular convolution. I am talking about the continuous time convolution itself. In graphical way, what you do is put the first. So let's say you need to convolve x of t and h of t. So you put x of t as something. This is, let's say, x of t. There are three steps involved if you remember. First is do inversion, then you do shifting, then you do multiplication, and then you integrate. I hope you remember
Yes,
it
sir.
from
Yes,
signals
sir.
and system.
Yes,
Yeah,
sir. Yes, sir. Continuous.
correct.
Yes, sir.
So using this concept that the output of the filter is calculated by convolution, and using the concept that convolution can be done using graphical way. So these two are hints with which you can solve this question. Okay, now you have to see like in what scenario this complete thing will be maximized. So from there, I think you should be able to solve this question. So, if you want the answer to this, the answer to this is a square wave of frequency omega naught. The answer to this I can tell. The answer to this is the square wave of frequency omega naught, and hint I can tell that this is the hint. Now you can solve the question.
Okay, sir.
Okay, so
I will
try
try
it.
and complete it, sir.
Try it. Because exact solution we are not supposed to give. So I hope that this hint helps you. Okay. So any other doubts?
So one question here.
Yeah.
So while working this, it may not be clear which waveform we should choose for x of t, which will get the peak output, right? So
Correct.
you have to find the inverse function of this. So is there any straightforward way to approach it? Because you're trying to find the maximum of that x of t convolved with h of t, the peak
Uh,
maximum,
no,
right?
maximum of x of t convolved with h of t in time domain. So I will make this a little clearer. In time domain, at any instant of time, you have a time domain signal at any instant of time. Let's say there is some maximum, okay, that can come at any instant of time. So you need to find the peak value of the peak value of this thing in time domain should be maximum. You should think, so let's say for some x of t in time domain you get something like this. Okay, for some other x of t you get something like this. Okay, for the first x of t, the maximum, the peak value is this thing. Okay, the for second x of t, the peak value is this thing over here. Now, which x of t gives you the maximum value? This is this x of t. Okay, so this x of t you need to find. This is what is needed from the question. And the hint that I said you, you should view it in completely in time domain. And other thing is, you should view convolution as the graphical convolution. This should give you, if you try to uh, uh, view it in this direction, it should give you what should be the answer to this question. And the answer to this question, I will tell you that I can tell that is a square wave of frequency omega naught, and square wave with without any DC signal. There is no DC signal in it. It's just a square wave with frequency omega naught. This will give you the maximum thing.
Sir,
So
for
yeah.
week 5, question number 2, sir.
Okay, let me come to that then. So we have week 5. Okay, so this is question number 2 you are asking, right?
Yes, sir, exactly.
So this is extension to question number 1. So in the filter of previous problem, replace the op amps used with integrators only with a VCVS, but dominant pole compensated model with unity gain feedback of this thing. So this right? The one that have omega naught by S kind of transfer function. Can you see my screen?
Yes, sir, yes, sir.
Yeah. So omega naught by S kind of transfer function is what they are talking about. So this I hope you know. And then calculate and verify the peak magnitude response of the filter. So peak magnitude response, how will you calculate? So you know how much quality factor distortion happens, right?
Dynamic range scale.
Due to limited. No, not dynamic range scaling. Due to limited bandwidth of this has limited UGB, right? So omega naught. So let's say it's some omega u. You have omega u. You have for an integrator. Let's say you have for a biquad. Let's say you have some omega naught. So given that you have omega naught, given that you have omega u, both of the things, there is a relation that gives you the distortion in quality factor, right? That has been explained in the class.
Sir, can you get that one, sir? I mean, I cannot relate it. Explain.
Sorry. Uh,
Can you please explain about that relation, sir? That omega naught and omega gain.
uh, I don't remember the exact relation. There is a so let's say you have some
Yeah, it is
quality factor
near to
Q
the
hat.
imaginary axis. Yeah, yeah. Sir.
Yeah. That complete the analysis that at the end of that complete analysis, you have a relationship between. So it's something like this. I don't remember it exactly.
Yes, sir. Yes, sir.
Omega U into 2Q, something like this. So uh, I hope this is the one. Can someone confirm? Is this the relation?
Yes, sir. This is the relation only, sir. I have written a note, sir. Not exactly, sir.
So okay, whatever the relation is, this relation you know, right?
Yes, sir.
So this
Not,
relation
sir.
you know, now you know.
Not relation, sir.
Uh,
Okay. Means before that there would be a theory, no, sir. Need a theory, sir.
no, that theory you can watch the lecture again, no?
Okay, okay, sir. I mean, sir, I mean, sir, any point means I will get it here, sir. That's why, sir.
Sorry, no. You can watch the lecture. That theory, the lecture is detailed. That will make if you watch the lecture, you will get to know. Now the same analysis, like how did we do the complete analysis? We did we calculated, we did the analysis for simple integrator first, correct?
Hmm.
What we did, we replaced the ideal op amp with omega naught by S model, correct? In this
Yes, sir.
integrator. Then we did the transfer function analysis, and we got some integrators response that was 1 upon SRC into some additional function, correct?
Okay. Yes, sir.
Yeah. So with that, we said that we will replace S by S into this additional function, correct?
Okay. Hmm.
And then when we replaced it in the actual with this we said that there is this imaginary axis along which that imaginary axis shifts, and from there we calculated the enhanced quality factors, correct?
Yes, sir. Yes, sir. Oh, yes, sir.
Yeah. So you can go there and revise. So this was the complete process. Now, what actually you need to do, the peak response. So let's say the quality factor is significantly high. Okay. In that case, the peak response will come at omega naught, and that will be equal to 1 by cube. So the approximate value of this peak response can be calculated as, so you have n number of biquartz in cascade. So the peak response will be Q1 into Q2 all the way to Qn. Okay, this is it won't be the exact peak response. Exact peak response will be somewhere different, but this will be approximation of that. And like in the first case, you can show that you will see a peaking in the overall magnitude response due to the finite bandwidth effect. However, when you put this transfer function, so what will be the value? What will be the value of this transfer function? Can you comment on this? Like, what will be the transfer function from this op amp?
From this open, sir.
It will be omega naught omega u square by s square, right?
Yes,
Because
sir.
you have sorry, it won't be omega. So omega u square by s square plus some additional term to do this compensation thing. So yeah, basically, what when you do this complete thing, no, like you put this complete thing in the integrator and calculate the integration transfer function, you will see that the this over here, like approximately, will almost become to 1. Okay, so what you will see is you are getting near ideal transfer function, like even after having a finite bandwidth in each of the individual op amps. Okay, why this is happening is like there is cascade of two op amps, right? So
Yes,
like
sir.
at least in the frequency of interest, the overall response, the overall gain that this op amp can give has increased. So in that case, what you will find is the integrator's transfer function is nearly equal to the ideal one. Hence, there will be no quality factor distortion. So you won't the peaking that you were seeing with only omega u by s. So this is basically the complete procedure that you need to follow. So if you follow the math, you don't have to do apply much of your thinking. All what you need to do is just replace the transfer function of omega u by s by the transfer function of whatever op amp, whatever this contraption gives you, and with that, basically you follow the complete procedure that has been done in the lecture, and you will by yourself see that you will get the response of the integrator that is nearly equal to the ideal one.
Yes, sir.
Okay, so you can try it out, and I hope you will be able to uh, find the answers.
Yes.
So, any other doubt?
Sir, in week 6, sir,
Just a
last
minute.
problem, last problem,
Uh,
sir. I think problem 6.
Weeks is the deadline over?
Yes, sir.
The
Deadline is over,
deadline?
sir. 5
Okay, fine.
question, not 6. 6.
Last
Question number
problem.
5.
Okay.
Yes, sir. This last problem is that content is delivered in week 7, sir. That problem is given in week 6, sir. Today only I
Uh,
confirm.
no. This the one the final the Bode-Noise theorem that gives you that the capacitance at zero and capacitance at infinity kind of thing, that is covered in week 7. However,
Before
the
that, there
energy
is one more
concept.
video, sir. They in that video only entire thing is discussed, sir.
No, but that energy thing is already the Nyquist noise theorem has been discussed, right? So this question can be solved with the Nyquist noise theorem, right?
Yes, sir. But week 7, that if I watch that video, I get full clarity, sir. Actually, in
Okay,
week 6.
no, the point is that this question can be solved with Nyquist noise theorem as well, that kT by C into energy of
Yes,
zero
sir.
minus energy of infinity. So
Yes, sir.
use that Nyquist noise theorem and solve this question.
Yes, sir. Yes, sir.
That is
Sir,
the
in
bottom
that
line.
also, why professor take only 1 coulomb, sir? Is there any specific reason, sir?
No, you are taking unit impulse. No, unit impulse. How much charge that unit impulse would have? Let's get back to it. So 1 coulomb is basically the overall charge that unit current impulse has. So how do you visualize a impulse function? So an impulse function is something that is of a very short duration. Let's call it delta. Okay, in time, and its magnitude in that short duration of time is 1/delta. Correct. So
Yes, sir.
what is the total area of this? 1/delta into delta.
1 1, sir.
So if now this is the current, this is the unit impulse current that you are transferring into this thing. So what will be the y-axis in this? Amperes, right?
Yeah, yes, sir. Yes, sir.
Okay. So what this area will signify? Area under the curve of a time of a current
Impulse signals
waveform.
is 1 1,
What
sir.
does that signify? No. What does that signify? What physical quantity area under curve of a current signifies?
I'm not getting, sir. Can you repeat again, sir?
So there is a current waveform with time.
Yes, sir.
So this is, let's say, some I. If I take area under this curve,
Yes, sir.
this area, let's call this A. What does this A signifies?
Means it is band limited to means it is band limited to delta.
It is. the band limit is band and all cannot be. This is completely time domain. This
Okay.
is not in frequency domain.
Okay, sir.
Integration from minus infinity to infinity of a current waveform with respect to time.
Yes, sir.
What physical quantity is this?
I dq by dt, sir. It is I is equal to dq by dt, sir. It is
Yeah, correct. So this is
charge, sir.
charge.
Yes, sir.
Okay. So what does the area under this curve signifies?
Charge, sir. Q.
Yeah. So how much charge is it?
Um, so, I think one, sir. In
Yeah,
in
one
this,
coulomb.
yeah, 1 coulomb, sir.
Correct. So that's how you get this 1 coulomb thing over here. I hope this is clear to you now.
Yes, sir. Yes, sir.
Yeah. Just a minute. Just a minute there.
Yeah. Okay, sir.
Yeah. Am I audible?
Yes, sir. Yes, sir. The screen
Okay.
is not visible, sir.
Hmm. Uh, yeah. So I hope this thing is clear to you.
Yes, sir. Exactly, sir. Sir, I mean,
Yeah.
I'm confused. Sir, in total integrated output noise, while finding total integrated
Okay.
output noise, question number.
Which question you are talking about?
Sir, I think. Yeah, sir. Question number 4, sir.
Okay.
So first question number 3 did, sir. For question number 4 means first we need to find out the equivalent note, sir.
Okay. So a hint for this I can give. You know what integral you need to find, right?
Sir,
So
let
let's
me
say you
check
calculate.
one more thing, sir. I'm doing correct process or not? Just confirming, sir. Can you,
Okay. Yeah. Uh, Please tell.
sir? For question number 1, first initially we need to find out the that gain, sir.
Wait. Let me. Which question you are talking about? Question number 4 or question number 1?
Question number 1, sir.
Okay. In question number 1, what do you want to know? Wait. Let me bring it to the.
Sir, or else, sir, can I mail my solution, sir? You can see where I commit a mistake, and I will correct it, sir.
Okay, you can do that. Fine.
Yes, I will mail it to you.
Hello.
Yeah.
I have one question in this week 3 assignment. How That problem 2 can be arrived.
V3.
Yeah.
Uh, just a minute, I will put it. So I hope you can see the problem.
Yes. Okay, see.
Yeah. What you need to do is the phase transfer function has been given to you. Correct, and you need to find the linear, you need to show that for linear phase response, the first two conditions are as follows. So now I hope you understand the significance of linear phase response. Do you understand it?
Yes, that phase delay.
Yeah, constant delay should be there for all the frequencies. Correct.
Correct.
So, what does this mean is linear phase response means that your transfer function, your this complete function derivatives, first derivative should be a constant, and latter derivative should be zero, right?
Hmm.
Yeah. So, for the so what you can how you can proceed is that you can calculate the first derivative, and in the first derivative, when you calculate the first derivative, it will be based on some alphas and betas and omegas, right? So how you can write it? You can write it is in the form of 1 plus omega square plus omega to the power blah 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 till infinity it can go. So what you need to do in that is all the apart from in the first derivative should be constant. It should have no omega in it. So you should one by one make the coefficients of each of the uh, omega's power that is not equal to zero. All those coefficients you should make as zero, and from that you will be keep on getting these relations. So the first two relation will come out to be this.
When you say expand it, right? So first we need to bring this term out.
No, no. Take the derivative. The derivative of this complete. Okay. So let me do it in the following way. So phi you have, and then what you need to do is, so if you wish to take the derivative of this, what you will have is 1 upon. So it's minus tan inverse some f of x, right? F of omega. Sorry. So its derivative will be minus 1 upon 1 plus f of omega whole square into f dash omega, correct? I hope I have written it correctly. And
1 by 1 plus
now
x square
in
into
now
derivative. Yeah, correct.
yeah. So now this will be either you can use Taylor series or some sort, or you can work out the math. So this will be some kind of polynomial in X due to the Taylor series and all those things you can see. So this will be some 1 plus some C1 into omega plus C2 into omega squared and so on. Because this is also a polynomial, this is also a polynomial. So you can write the Taylor series for this thing. So these coefficients C1, C2 and all those things you should put as 0 to keep on getting the conditions.
Okay. So we will have one equation is d phi by d omega is a constant, and second equation is higher derivatives
Yeah,
are all zero. Those are the two
0.
conditions we will
Yeah.
need.
So I don't think you will need to go to higher derivatives, because if you keep on, so I think these here only you will get multiple constraints, right? Like the C1 has to be 0, C2 has to be 0. Now this C1 will be some combination of alpha 1, alpha 2, beta, and all those things. So from there, I suppose you will be able to get these relations.
Okay.
Yeah.
And the question one in this is also not very clear. This assignment. How to
Okay.
clearly proceed with this?
So question one. Wait. Let me put question one also on the.
Sir.
Yeah.
Sir, I already made week 3 also, sir. Can you please check, sir, is it correct or wrong?
I will check it. Can we
Week 3
take it
by week 3
offline?
also, sir. Week 3 also, sir. What you are discussing now, that you know.
Sorry. So you have mailed where?
To your mail ID, sir. All previous session, I take your mail ID.
Yeah, that's what we can check. We are not supposed to discuss the exact solutions. Like we can give the hints, we can tell you the answers, but exact solutions we are not supposed to discuss. So we will take it offline later. Okay. I
Yes.
hope this is okay.
Yes, sir.
Yeah.
Don't say. Means if I commit any mistake, no, sir. After that, my assumptions I will change, sir. That's why, sir. Just have a look, sir.
Yeah. So that's what I will take it offline.
Yes. Okay, sir.
In this case, the in the class we did in the class the analysis was did for maximally flat at 0, but now this maximally flat has come to instead of 0 it has come to some other frequency, that is omega naught, correct? Again, the same things you should do, like apart from the first derivative, all the derivatives you have to assign it to as 0. And again, here the hint is which is the series of like, let's say you have any function, say f of x, you can always expand it in Taylor series, right? And in Taylor series, how does a Taylor series look for, let's say you have fx. So how does this look? Let's say it's some fx plus a. Okay. So how does this look? It looks like f of a plus x times f dash of a plus x square by 2 factorial, right? This is how a Taylor series looks like. You have these coefficients. So you can put them 0, 1 by 1, and from there you can find the. So basically, for maximally flat at x equal to a, what should be the condition? All these derivatives should be 0. So from there you can find the what all things that you need to find. These restrictions and all you can find from there. I hope this is clear now.
Sir.
What about
Yeah.
that? What is the restriction on order of f of omega square?
So you will be able to find it out from this only. Like there will be some the things that you should keep in mind, that magnitude response should always be greater than 0 and all those things. So if you consider those, because magnitude response can't go less than 0, right? The square of magnitude response. So that should take care of that the restriction that you get on order of the filter.
Okay.
Yeah.
Sir, in this case, minimum order will be 2, sir.
I don't remember the exact solutions. I think the solutions are provided on the website, right?
Till now, we didn't raise any, sir.
Those will be the not the solutions. The answers will be there on the the NPTEL website soon.
Okay, sir. So for week 6, you check, sir.
Week 6, check what?
I already mailed to you, sir. Week 3, we'll talk offline, sir. Week 6.
No, in week 6, what do you exactly want? So that's what we are not supposed to discuss the exact solution. So, if you want to clarify any specific doubt, you can tell. If you want, uh,
Yes.
complete, let's say, complete this thing on that, we can take it sometime offline.
No, no, sir. Am I in correct path or not? That thing, sir. If you see, no, if you point out mistake there, you did. I will correct that point specifically. I make a work on that, and I will improve. So that's what.
Okay, so that's what. Can you tell? Uh, wait. So in week
From my
6,
point of view, I am very correct. That's how thinking. That is not correct, no, sir. You, if you uh, think, see, there you lag in that. If I will work on that, I will improve, sir.
no, no, wait. So let's bring this thing over here. Okay, so this is so the problem one, determine the output noise voltage spectral density. I hope this
Yes, sir.
should not be a problem. This is like done several hundreds of times. You can use any theorem you want. You can calculate it directly. You can use reciprocity. You can use inter-reciprocity. Whatever you want, you can use. This is just asking for spectral density. So there should not be an issue. Second is repeat problem one for second circuit. So
Inverting, sir.
again, this should also be straightforward. Then network shown in figure 4, it has this transfer function. Determine G omega naught Q in terms of circuit parameters. Again, this should be, this is like simple algebra only, and there is nothing specific in this. Second
Four,
part is,
four problems I did, sir. I get the answer also. Means if I commit any mistake, no, you will point out. Means there, I will improvise, sir. I will go once again the lectures, and I
no,
will.
see, what exactly determine output noise voltage spectral density a total integrated noise.
Yes, sir.
So, see, most of this part is straightforward. Determine G omega naught Q in terms
No,
of
no, sir.
circuit
I mean,
parameter. That
four
is
questions I
simple.
solved, sir. Four questions I solved, sir.
Okay.
Means four questions I solved. Fifth question also I make, sir, what I know. For four questions, if I commit any mistake, where means if you point out that mistake, I will improvise, sir. That
So that's what. Let the solution and evaluation of it come. No, there you will be able to see what mistakes. So after that we can discuss, right?
yes, sir. But exam is coming close, no, sir. 29th April. I have a few more exams. Means I have to work daily.
No,
That's
what I am saying is like, see, if there is any specific doubt, I can clear. Now, I cannot do this that you give me, there are 3,000 people in this complete course, and I can't just go and check the solution for each of them and point out that, okay, this is the mistake that you created, this is the mistake that you created. You tell me, if there is some doubt in some, if you see, most of this is straightforward. If there is simple math involved, for example, calculating the transfer function or calculating the spectral density, that is simple math involved. If there is some complexity in some question that you feel that, okay, is my thought process correct in that or not, so those
okay,
things you
sir.
can ask.
Yes, sir. For question number one,
Okay.
so for question number one, that input is given to non-inverting terminal, sir.
Okay, yeah, correct, non-inverting terminal it is given.
Yes, sir. While calculating the noise spectral density, that is 4
Hmm.
kT R1 into h of whole square, so modulus of h of whole square.
Yeah.
Sir, we have to include both resistors or we have to include one resistor, sir.
No, you have to include all the noisy elements, and both the
Means
resistors are noisy elements.
Yeah, for problem 2, only R1 will be included also.
No, why? So here also you need to find the output noise voltage spectral density. It's the output noise voltage spectral density. So it's a routine procedure. So let's say first of all you will find the noise due to R1. So you
Hmm.
will find the transfer function from here to the output and then multiply 4 kT R1 with that. The same thing you will do. You will find the transfer function from this voltage source to the output. You will multiply 4 kT R2 with that, and that will be your noise spectral density. The same exercise you have to repeat for the problem 2 as well.
Means that means the noise spectral density will be only for KTR2 into HF modulus of HF whole square, sir, for problem 1.
No, it's complete noise spectral output noise spectral density. Both of them will contribute to the output noise spectral density. So it will be for both of them. It will be for R1 as well as R2. It won't be like only R1 or only R2.
For problem 2 also same thing, sir.
Yeah, correct. So any other doubt
Yes, sir.
in any other question? If there is any specific the point where you feel that you might have committed mistake, you can ask. Like straightforward things, so calculating the transfer functions and all those things, like are mechanical things. Those I don't think that there will be any doubt in that.
Number 3. Sir, in question number 3,
Okay.
while calculating the total integrated output noise,
Hmm.
sir, means we have to draw equivalent for inductor also, sir. Means that generator and the equivalent capacitance, and for resistor also we have to draw that
No, no,
equivalent.
no. Whatever is given to you, you can
Hmm.
apply the Nyquist noise theorem and calculate the total integrated noise.
I mean, see, there is no, we need to draw the equivalent, and with that, with regarding this, we need to don't need to calculate the total integrated noise.
Uh, Equivalent what? There is, this is the circuit that you have. There is nothing. So you are talking about that the GMC gyrator you are talking about, is it?
Yes, sir. Generator and in series with the
No, no,
capacitor.
no.
Uh,
That is completely different concept. That is basically the way you emulate an inductor in a IC. Because inductors are bulky, you can't. Most of the times, you can't put physical inductors, so you emulate the inductor using GMC or active RC. That is a completely different thing. This that has nothing to do with this question. In this question, you have been given an RLC network, and this you need to find the noise.
okay, sir. For to determine the G and omega naught Q, we need to draw that. No, sir. We have to emulate, right? Means
No,
to determine the
you need to
gain and
find the transfer function. Yeah, this is the impedance that this provide is SL. The impedance that
on the
this
AC.
provide is 1 by SC. Now
Okay.
you are just to find the transfer function from here to here, compare the transfer function from this thing, and then calculate what is omega naught in terms of RLC, what is Q in terms of RLC, and what is G in terms of RLC. That's it.
Means no need to draw that capacitor equivalent, and there from there we need to find out the G
No,
and
no,
omega
no.
naught Q.
You don't need to. No, no, no. You don't need to do that. G over here is the gain. L. So yeah, basically, no, that and all you don't need to find. So you should be good with this.
Okay. Means
So G
for
is G will have some frequency dependence. So when you calculate the transfer function, I think you will be able to understand what frequency dependence is that.
yes, sir. If it is directly means that means inductor and capacitor are formed with series. We will find out the transfer function. With the transfer function, we will get that means h of s. From there, we will find out directly. That one is
Yeah, you will compare G with
standard.
whatever you have in your transfer function. You will compare omega naught with whatever you have in your transfer function. All those things you will compare and you will find.
So, okay, what I did, sir, from the class, the professor has taught that G equivalent for inductor, and
No,
that's
no,
how.
that no. That and all you don't need to do. You just need to straightforward find the transfer function of this network and compare it with the transfer function given in the question.
Okay, it's 25. Means that okay. Means I thought that professor taught in a week like this. That's how I did. So, okay.
No.
Means
You don't need to do all that. That is basically a practical implementation of inductor. That is nothing to do with this question.
okay. Means we don't need to means what the lecture means we don't need to draw that equivalent inductance and with
That's
this
what
we
you
can.
don't need to draw. You don't need to draw.
Okay, sir. I just confirm it, sir. So, okay, sir. Okay, sir. Yeah, now come to it. This week, sir.
Any other doubt?
Nothing, sir. No perfect, sir.
Okay, so I hope all the doubts are cleared. If all the doubts are cleared, then yeah. Apart from that, one concept we can discuss over here. So we discussed the KT over C noise thing, right?
Yes, sir.
We said that we calculated the total integrated noise of this sampling system, and we said it's independent of this resistor. It's just KT by C, correct?
Yes, sir.
Yeah, so this can also be done in time domain. Let's say if we want to do it in time domain, how we will do it? So you know that what is the inverse Fourier transform of power spectral density? Do you guys know this?
Be the autocorrelation function. Autocorrelation.
Correct. Yeah. So in frequency domain, the power spectral density you calculate as 4 so let's not go to 4 KTR. 4 KTR is the one-sided power spectral density. The two-sided power spectral density is 2 KTR. This passes through some filter of let's say some magnitude, and you get the power spectral density as h omega magnitude square times 2 KTR. Correct? Now, if you want to find the power of this, what you need to do is you need to find the complete integration under this curve. Let's say you want to find the power through autocorrelation function. Do you know how to find what is the power of the autocorrelation? What is the power? What quantity signifies the power in the autocorrelation function? Can you tell? So its Fourier transform will be some autocorrelation function, and autocorrelation function for a real system will be a symmetric something. Let's say it's something like this. Okay, here is tau. So the power of this is basically integral of this complete power spectral density. in time domain, in autocorrelation function, which quantity of this autocorrelation function signifies the power? Can you comment on that? The integration of from minus infinity to infinity of PSD times d of f is equal to what in time domain?
Integration of the autocorrelation function over the entire.
No, no.
Okay,
In
okay,
time
okay. It
domain,
is a
it's
DC
equal to
DC value of that autocorrelation function.
not DC, not DC at t equal to
T equal to
0.
0.
At t equal to 0, correct. So now let's say, so this is the power. The Rxx of 0 is the power, correct? So what we have is, so now let's say this thing is being sampled. So whatever output is there, that is being sampled, okay, with some sampling rate Ts. Okay, so you will get earlier you were having some continuous time noise, now you are having some discrete time noise. Okay, so in discrete time also you have autocorrelation function. Now the relationship between the continuous time autocorrelation function, so relationship between the time t and the numbers, the indexes n over here is what? N is equal to some tau by Ts, right? Where Ts is the sampling rate. So Rxx of n, that is in discrete time, will be equal to Rxx of n time Ts, where this Ts is where tau is equal to n times Ts of the continuous time autocorrelation function. Is this clear?
Yes. Okay.
Yeah. So, what happens over here then? What we do is, this is the thing we get, right? This shown in the pink is the discrete times autocorrelation function, correct?
Okay.
Yeah. So at now in discrete time, what will be the power? The power will again be Rxx of
0.
n when n is equal to 0. So we see that irrespective of sampling time, whatever sampling time we choose, this Rxx of 0 will never change, correct?
Yes.
Yeah. So with this, this is a mathematical way of showing that irrespective of sampling time, the total integrated noise power always remains the same. So it doesn't matter whatever sampling time you choose. If you integrate it in digital, in digital frequency domain, that is from 0 to 2 pi, the power that you get will always remain the same. The power spectral density might change depending on the aliasing and all those things. However, if you integrate it, it will always remain the same. And that is because that explanation can be easily understood in time domain with this approach. So yeah, this is one thing that you can keep in mind. So any doubts in this? So yeah, if there are no other doubts, so we can end the session for today. There is no doubt, then okay. So we will end the session. Yeah, is it okay with all of you?
No, 1 minute, sir. 1 minute.
Okay, fine.
In theory, sir.
Okay.
Sir, in theory, noise factor. I think this week at the amplifier stage, sir.
It is of which week?
This week only, sir. Not assignment related. The content related, sir.
Content related. It's in week 7, is it?
Yeah, week 7, sir.
Okay, so week 7 can we discuss in the next week? That will be better because I will also go through the lecture one, so I can handle your doubts better.
Means that noise factor means not and only one relation, sir. Not the entire thing. Only 2 points.
Okay,
While
so
at amplifier stage, while connecting after concluding that VA and IA correlated.
that's what I don't know exactly what you are referring to. Can you draw something and share your screen?
Oh, sir. Sir, in chat box, I can't insert image, sir.
Sorry.
In chat box, can I insert image, sir?
You can share your screen. I will make you a co-host and you can share your screen.
Oh, 1 minute, sir. One minute, sir. 1 minute, sir. I'm downloading, sir. Sir, this one and this one, sir.
Can you rotate it 90 degrees? There is, I think,
Sir, you can say that these two pictures also, sir. One and then next.
so can you rotate it? I think there is from second. Okay, so what is the doubt in this?
Sir, I mean, that noise, all noise sources are activated while taking that relation. No, sir. Vn2 is greater than Vn1. I'm not able to understand, sir, this concept.
Uh, so, so that's what I don't know exactly what you are talking about when you say VN. Okay, VN2 and VN1 are noise at the input and noise at the output, is it?
Yes, sir. All noise sources are activated.
Okay, all noise sources are activated. Then
In case one
what
means
is
all
VN2 and
input.
what is VN1?
The professor consider two cases, sir. In case one, all noise sources are all null. I mean, noise sources are not activated, sir. In VN1, VN2, all noise sources are activated, sir.
Okay,
With this relation, I mean, Vn2 is greater than Vn1, and Vn make with this relation, that Vn2 by Vn1, that means square noise is greater than one, like that he discussed, sir.
okay. So,
What I understand
if,
means, if, if it is all noise sources are not activated, and that means core noise would be less, sir. If all noise sources are activated, that means core noise will be more. With this relation, how came to that Vn2 square by Vn1 square?
so VN2 square and VN1 square, I suppose, is the RMS of the overall noise, is it?
Yes, sir.
Yeah, so when you have all the noise sources and all the noise sources are uncorrelated to each other. So how will you calculate the power of, let's say there are two noise sources, okay? Power of one noise source is P1, power of another noise source is P2, and they are uncorrelated to each other. So what will be the total noise power when both P1 and P2 are acting together?
Yes, sir.
That's what. So two noise sources are there. Noise from both of them will be uncorrelated to each other. This you understand, right?
Hmm.
Hello?
Yes, sir. I'm not able
Yeah.
to see. That's uh,
No, no, I'm not showing something. I'm just asking you, are you able to understand this fact that noise, noise from all the are uncorrelated to each other? This you understand or not?
yes, sir. This one I understand, sir.
Okay, if noise from all the sources are there are two random variables who are uncorrelated to each other. How will you find the RMS of random variable one plus random variable two, or power the sigma square of a random variable one plus random variable two? How will you find that?
It's individually find out, no, sir. That noise, uncorrelated
No,
noise.
you will. Yeah, you will find out. Let's say power like the sigma square for random variable one is some sigma one square, and the sigma square for random variable two is sigma two square. When you add these random variable one and random variable two, what will be the resultant variance?
Okay. Means before means that change, sir. The difference before
overall
activating.
overall resultant so there is a new random variable, that is random variable 1 plus random variable 2. What is the
Yes, sir.
variance
Summation
of this new random variable?
means it is summation of both, no, sir. It would be the max noise like that.
Sorry.
It would be the maximum value, sir.
No, I am not talking about the exact quantity of that. I am talking about the variance. You understand that the variance of two uncorrelated noise sources is the sum of the variance of those two noise sources. Do you understand this?
No, sir. Could you please explain it, sir?
Okay, so let me
Yeah.
try it
Can I stop it, sir?
explaining. Okay, So what is let's say there is a random variable called x1. What is sigma square, sigma 1 square? That is the expected value of x minus x1 minus average value of x1 whole square.
Whole square.
Correct?
Yes, sir. Yes, sir.
What is it for x2?
Same, so sigma 2 square expectation of x2 minus x bar whole square. If there is a correlation, means there will be, while convoluting, that would be means expectation of x
Yeah.
this
Wait,
plus this, that would
wait,
be.
wait, 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 wait. So this thing you understand, right?
Yes, sir.
Okay. So this you can write as x1 square plus x2 square. Let's say the mean is zero. The noise of the mean, noise is generally zero mean. So let's stop the mean. Okay. Let's say x1 bar is equal to zero and x2 bar is also equal to zero. Okay. So in this case, what will happen? X1 square plus x2 square plus x1 x2 plus x2 x1. Correct?
Yes, sir. Second order expectation of second order.
Okay. Yeah. So this you can write as expectation of x1 square plus expectation of. So in this case, if the means are zero, this is the expectation of x1 square, and this is expectation of x2 square. So the this you have, right. So now it will be expectation. The expectation of this complete will be expectation of x1 square plus expectation of x2 square plus 2 times expectation of x1 into x2, right?
Yes, sir. Exactly, sir. If there is a correlation, that expectation of x1 x2
Yeah.
will be present. If it is
Now
uncorrelated, means that would be zero.
this part will be zero if they are uncorrelated.
Exactly,
The
sir.
e times expectation of x1 into x2.
Yes.
Yeah. So sigma, the total sigma, the variance of the summation is variance of one plus the variance of the second part, right?
Exactly, sir.
So this is a positive quantity. This is a positive quantity. So the overall variance of the summation will be greater than each of that, right?
Sir, means while summation it would be greater than individual. Yeah, correct, sir.
Yeah. So that's what, if all the noise sources are not activated, there will be some sigma 1 square. If all the noise sources are activated, that will add some sigma 2 square. So, the resultant will be noise from the initial noise plus the noise sources that you activated later. Their summation will be the resultant noise. So, its variance will be higher than the individual, before, right?
Yes, sir. Exactly.
Yeah. So, that's why that relation came.
Yes, sir. Yes, sir.
Okay.
Sir, 1 minute, sir. 1 minute, sir. Don't get distracted, sir. Sir, from week four, from week four, we start from RC backward,
Hmm.
and from backward, sir, forgot to ask, sir. Sir, for RC backward is not used because of speed, sir. Or,
No, no, both RC bipod and GMC bipod both are used. Their applications are different. If you want high speed and you are not too much worried about distortion or the noise and all, you will go for a GMC bipod because that is completely open loop. But if you are not worried about too much speed, you are worried about precision and all, so then you will go for RC bipods. So application you can see in this way. Now, for example, you have communication systems, let's say 5G radio, 6G radio. There, or maybe forget about radios. The communication between let's say you have a computer, right? Computer has two chips, okay, and they have to communicate with each other. They will communicate in ones and zeros because a digital processor understand ones and zeros, right?
yes,
This
sir.
you understand, right? So there like if you are to transmit one, that means signal is there. If you are to transmit zero, that means signal is not there. You are not too much worried about, let's say you transmit one, and instead of one, you, let's say you don't get one, you get zero. 0.9 or zero. 0.8, then still you can understand that the signal you transmitted was one. Okay, or like if you transmit zero, if you don't get zero, you get some point 0.1 or minus point 0.1. Still, you will know that signal is zero. So that won't integrate. That won't affect you. The accuracy of the filter won't affect you that much. What actually we need is you should be able to do this very quickly. Correct? Because your processors and all are running at some 2.4 gigahertz. So you need to do this all very quickly, but you are not too much worried about the accuracy and all. So in this case, you will use GMC kind of filters, open loop architectures. Okay. But let's say you are working on some robotic arm or something. In industries, you have robotic arms and all. So there you need to do it very precisely. Let's say you need to fix at some angle. You need to fix the robotic arm at some angle, let's say 52 degrees. Okay, there you need to be 52 degrees exactly. Right, but there you don't need too much speed. The robotic arm can move a little bit slow, that is fine. So there you are more concerned about accuracy and not that much concerned about speed. So in that case, you will use this closed loop structures that are the active RC bipod. So these are this is just an example to show like where you can use GMC bipod or where you can use active RC bipod.
Sir, means if it is open loop system, that's how it came some non-linearity, sir.
Yeah, so in a closed loop in open loop system, what happens is the the GM that sir showed, right? They are made of transconductors. Okay, transistors. Now transistors are non-linear elements. They are not linear. You know the square law model, right?
Yes, sir.
So for MOSFET, there is it's not yeah, current is equal to some VGS minus VT, VGS minus VT to the power 2. So it's non-linear, right? And now if you put complete voltage source, voltage swing at the input of that transconductor, at output the current will be non-linear current. That won't be a linear function of the input voltage. So there you will get non-linearity. But in case of active RC networks, there is virtual ground, right? That op amp is made of these transistors, but since the input of the op amp there is a virtual ground, that node won't swing much. So that's why you don't see too much. You don't see too much non-linearity because that node is not swinging only. So mainly the processing that happens is through linear element, that is resistor. A resistor is a linear element or capacitor is a linear element. There V is equal to IR will hold in resistor. So that's why active RC network is more linear, but GMC network is less linear.
Sir, is there any relation? I means this one is different. Analog IC is different, sir.
Sorry.
In industrial perspective, means how they will relate, sir, that analog IC design and circuit analysis.
So for designing, you need to know how you do analysis, right? Without you knowing how to do analysis, how will you do the design? Both of them are related. So let's say here you learn about filters and all. Okay, learn how to design a filter. Then here you did block level things, like you assume that let's say you need to design second order biquad with some frequency of 100 megahertz. Okay, so from this course what you learned, that you can you learned how to do dynamic range scaling. You learned how to choose the value of input resistors, capacitors and all based on noise requirement, or based on bandwidth requirement and all these things you learned. You learned that what the op-amps high level specification should be, like what its UGB should be from that finite bandwidth effect, that you learned. Okay, and now you know that the op-amp needs to drive the circuit. Now, how will you design that op-amp? You will design that op-amp using some two-stage feed-forward compensated thing, or some Miller compensated thing, or some dominant pole compensated thing. Now, like each stage, how will you design? You will use some differential pair, or you will use some cascode or telescopic op-amp. All these things where you learn, learn in analog IC design. So this circuit analysis for analog designer mainly gives you some high level tools, mathematical tools, and with that you can calculate some high level specification. Now to exactly how to implement it on IC, like using transistors, that you learn in analog IC design.
That power management is advanced thing, no, sir.
Yeah, so once you know analog IC design, once you know circuit analysis for an analog designer, now what you need to do, you need to design an IC for a particular application. That can be an application of some power management IC, or that can be all these skills can be applied to PMIC, or all these skills can be applied to let's say a data converter or a RF chain. So those things are like one level up of these things. So those are application specific. So there you will learn another set of rules, or another set of basically constraints related to that particular application. So if you first of all you should focus on analog IC design and this course, and after that you can based on which application you have most interest on, you can choose you can go through any of those subjects.
Yeah, so that one is advanced course, no, sir.
Yeah, that is so that will have concepts of how
DC
to
to
design DC-DC converters, what are various control systems that are used there, and all those things. So that is application specific to power management only. There are few general concepts also, but yeah, mostly it's power management, and that is high level course, advanced course.
If you are enrolled that MTech, it would be in second year, sir.
At least in IIT Madras, the courses are completed in first year only. In second year, you do project. So 9 courses you have to complete in first year only. In second semester, that will be. Or yeah.
Sir, MS by research is different, sir.
Yeah, MS by research is a much more extensive program than MTech. MTech is a course-based program. The project component is not that extensive. It's mainly focusing on training you based on the courses. But MS by research is basically training you for doing research. That is more project-based course. So that is different from MTech.
Sir, while you are studying, you studied about op-amp and its practical applications also, sir.
Yeah, you will study all this in these courses only, analog IC design, or this CAD or PMIC. All those in all those courses, you will study all this.
Specifically, you study OPAM, sir. Means there will be differences, no, sir.
Yeah, the
For
specifically
ideal
you will
case and
study
non. Yes.
that specifically op-amp design you will study in analog IC design.
Oh, okay, okay. In week 8 and week 9, I understand.
Yeah.
My doubts are completed, sir. Thank you,
Okay.
sir.
Okay.
If
Yeah.
process, I mean, is there any possible of times of 1 hour in your free time, sir?
I will let you know. I will let you know.
Can I
In
mail?
the mail on. Yeah, in the mail I will let you know.
Yeah, sure, sure, sure. In your free
Yeah.
time only, sir. I mean, I
Okay.
will make
Yeah.
that schedule. Thank you, sir.
Yeah. Sure.
Thank you.
Thank you.